This is MAT5700 Lecture 36. Today we begin Chapter 6. We're going to start Section 6.1. We will not completely complete it today. We'll do most of it though. So Chapter 6 is about so-called joint distributions. And I'm going to give you an informal example. Suppose we have two. Let's consider the example of the following. So we have two random variables. You have a population, and suppose X is the number of cigarette smokers. So, and Y, let's say, is another random variable, which is the number of cases of lung cancer. Now, usually, if you're a researcher, you want to know the connection between two or more random variables. And so you might want to know, for example, whether there's what the probability is of X being at most A and Y being at most B. So the probability that there are A or fewer smokers in the population and B or fewer lung cancer patients or people with lung cancer. We're trying to study relationships between random variables, and this is the way to do it. So, let's talk about the discrete case first briefly. So suppose we have X and Y are discrete random variables. So you want to consider the following function of two variables, P of X, Y. It's called, which is given by the probability that X takes value X and Y takes value Y. So this is called the joint PMF, the joint probability mass function of X and Y. So the first question we can ask about this is, what's the relationship? How does this function of two variables relate to the probability mass functions P sub X for X and the probability mass functions function for Y? So that's the question. And the answer is very simple to formulate. But I need to clear the screen. Okay, so how's this going to work? Well, let's let x1, x2, etc. be the values that X takes. Remember, X is a function on the sample space. It's a real valued function. So I want to look at all the real numbers that are values of X. And similarly, let Y1, Y2, etc. be the values that Y takes. Okay, so then what is the PMF, the probability mass function for X of the random variable X? Well, what is P sub X of X given by? Well, that's by definition the probability that X is equal to X. But that's exactly the same thing as saying that the probability X is X and Y is less than infinity. And instead of writing and, usually the book writes a comma in place of and. See, y always takes value less than infinity. So, or maybe minus infinity is less than y is less than infinity. But what is that? Well, that can be written as a collection of distinct events. It's the same as the probability. We can look at the probability that x is x and y equals y sub j, and these are mutually exclusive events, and so y equals yj and x equals x. So where j is equal to 1 to infinity. So this probability is that, and so that's actually the answer, how to relate the probability mass function for the random variable x to the joint probability mass function for x and y. We sum up over the y variable. Okay, and similarly we have that p sub y of y is the sum, say I goes from 1 to infinity of the oh, actually, let me, before I do that, I want to erase this. A better way to write what I just wrote in the box is this. I can also write, and it's probably nicer to write it this way. P sub x of x is equal to the sum j goes from 1 to infinity of p of x comma yj. So that's actually the preferred way to write this, the thing in the green box. And similarly, what we have is the probability that the probability mass function for y at y is given by the sum I goes from 1 to infinity of p of xi comma y. Okay, so that's how that works. Okay, so I think I'll just do an example, a simple example, on the next slide. Okay, so here's a chart. It's a sloppy looking chart. I have two discrete random variables, x and y, and the chart indicates p of xy for various values of x. So you have p of x equals 0, y equals a p of 0, 0, for example, is equal to 1/6. P of 0, 1 is a quarter, etc. So the first thing that's always true for the joint probability mass function is if you sum up over all values of x and y, p of xy sums to 1. That's actually, I should probably write xi, yj. So let me write it like this. These are the allowed values of x and y. So let me write it like this. Xi, yj, where we sum over I and j. That's something that's always true for every joint probability mass function. Okay, and you can see that's true in the table. We add up all the values in the table, you're going to get, well, you got 3 copies of 1/6, which is 3/6, which is a half, and you have a copy of a quarter plus 2/8, which is also adds up to a half. Half plus a half is 1. So that's always true. So now here are some problems we can solve with this. Let's compute the probability that x equals 0 and y is less than or equal to 1. So how do we get that? Well, the probability x equals 0 and y is less than or equal to 1. Y only takes 3 values, 0, 1, or 2. This is the same as p0, 0 plus p0, 1. And p0, 0 is a sixth, and p0, 1 is a quarter, and a sixth and a quarter is what? That's common denominator of 12. It's 2/12 plus 3/12, which is 5/12. So that's a question we can ask and answer. So let's now compute the actual probability mass function for the random variable x. So what is that? Well, we have to, x takes value 0, 1. So what is p sub x of 0? We need to know what p sub x of 1 is. So what do you get? So p sub x of 0 is going to be given by the sum of p0 y, where the y's vary, p0, 0 plus p0, 1 plus p0, 2. And that's going to be given by the sum of the rows in this, so 1/6 plus 1/4 plus 1/8. And that should be what? Well, we saw that's 5/12, which is 5/12, which is 10/24 plus 3/24. It's 13/24. So that's p sub x of 0, and p sub x of 1 is the sum of the entries in the second row. That's 1/8 plus 1/6 plus 1/6, and I believe that should be um, 5/12. No, is that right? No, it's not. Let's see. So it's 1/8. So uh, so what? So that I think is 11/24. So that gives you, that tells you what the probability mass function of the x variable is. You can similarly figure out what the probability mass function of the y variable is. The value at 0 is the sum of the entries in the first column. The value at 1 is the sum of the entries in the second column, and so on. Okay, so that is an example. Okay, so what I want to talk about, though, and we're mostly interested, is the continuous case of all of this. So I need to clear the screen now. So let's talk about the continuous situation. So we're going to need a definition in the continuous case. So let me give it. So let's consider x and y continuous random variables. And if there exists a function, f of xy, so it's a two-variable function. Now remember, two-variable functions you integrate over regions in the plane. Maybe called the region E. Okay, so then we'll say that if there exists a function f of xy such that the probability that x and of xy lying in C is given by the double integral over, I'm sorry, not C, but E of f of xy dA. So in that case, we say that, so first of all, you need to know the function's integrable. We'll say this is a joint. We say in this case that f of x f of xy is a joint probability density function for x and y. Okay, so typically the kinds of regions we're interested in, typically interested in cases when E is a rectangle or E is an infinite strip, like minus infinity, infinity times CD, or an infinite strip of the form AB times minus infinity, infinity. So in the second case, for example, that looks like an infinite strip going like vertically. In the former case, it's an infinite strip going horizontally. Okay, so that's the definition of the joint distribution for two random variables. So we need to have a joint probability density function. If we have that, we can associate other quantities, other functions. For example, the analog of a cumulative distribution function makes sense in this case. So let's talk about that. We have the so-called joint the joint cumulative, or maybe it's the cumulative. Let me write it like this: joint cumulative distribution function associated with the joint density function. So I'm going to just write joint CDF from now on. That's going to be given by the function of two variables, f of a, b, where you're going to integrate minus infinity to b and minus infinity to a, f of x, y, and we're going to integrate first over x and then over y. So that's the definition of the joint cumulative distribution function. One also can recover the density f of xy from capital F of xy, where what we do is we take, this is just by the fundamental theorem of calculus applied twice, we're going to take the second partial of f at xy with respect to the mixed partial dx dy. So that's good to know also. Okay. We also have the associated so-called marginal density functions. These are just the probability density functions for x and y separately. So what is it? So f sub x, this is, we can derive this, but it's by analogy of what we did in the discrete case. We just sum up over all values of y. So in other words, summing means integrating. So we're going to integrate from minus infinity. We're going to treat the function as a function, which is a function of two variables. We're going to integrate with respect to the y variable, and what's left over is a function of x alone. And similarly, we can actually define the marginal PDF for the variable y as the integral from minus infinity to infinity of f of x, y, dx. So these are something we're typically interested in. Okay, and we even have we can even sort of decide more general questions. For example, we can consider the probability that x lies in maybe some interval or something. We can answer questions like that. What does that mean? That's the same as the probability that x lies in A and y is between minus infinity and infinity. So that's the same thing as the integral from the integral of x in A and y going from minus infinity to plus infinity of f of x, y, dy, dx. And so we can think of it that way, and this is the same thing as this. So that's what it is. Okay, there's nothing more to say about that. Similarly, we can say something about the probability that y lies in some b along the vertical, along the y-axis, as being the probability that y is in b and x is going from minus infinity to infinity of f of x, y, dx, dy. Okay, so y would be in b in that case. Okay. I think it makes sense to just do an example. That's really the most helpful. Okay, so so here's an example. So let's consider the function f of xy, which is given by 2x plus y over 210, where x is going between 2 and 6, and y is going from 0 to 5. And then it's going to have value 0 otherwise. So this is a distribution that is supported on the strip x going from 2 to 6 and y going from 0 to 5. So it's on a rectangle. This is the rectangle it's supported on. Okay, so why is it a, first of all, a joint distribution function? Well, we can integrate this over the rectangle. So let's call the rectangle E. Well, if we integrate this, that's not what I wanted to say. If we integrate this over all of R2, so that's minus infinity to infinity, minus infinity to infinity, f of xy dA, that's the same dx dy. I should write dx dy, say. That's the same thing because the function is 0 outside the rectangle. It's the same as the integral from 2 to 6, 0 to 5 of 2x plus y over 210 dx dy. And if we integrate this with respect to x first, we get the integral, the antiderivative. So you can break this up as 2x over 210 plus y over 210. And the antiderivative of 2x over 210, I'll bring the 210 out, is x squared plus y times x, where x is going from 2 to x equals 6. And then we have to integrate that with respect to y. And that's 1 over 210, the integral from 0 to 5 of what? 36 plus 6y dy. Oops, that's no good. I have to subtract off the value at 2. So that would be 2 squared is 4 plus 2y. And then we integrate that all with respect to y. I'm going to first simplify 1 over 210, integral from 0 to 5. 36 minus 4 is 32. And that's 6y minus 2y, which is 4y dy. And this is 1 over 210. 32y plus 2y squared, evaluated from 0 to 5. And this is 1 over 210 times 32 times 5 plus 2 times 5 squared, which is 50. And so what do we get? We get what? We get 210 over 210, or 1, and that's what we needed to check. You see, this function is positive, is non-negative everywhere, and its double integral over the whole plane is 1, and that's what it is enough to guarantee that this is going to work. This is actually a joint probability density function, and that's what we have to show. Okay, so that's great. So let's ask some more questions about this. Okay, so this is, I just copied on this new slide the function we had on the previous slide. And let's calculate, just for fun, or maybe not for fun, maybe for torture, let's find the marginal probability density function of the random variable x. So what that is if we're going to do this at x, that's the integral from minus infinity to x. This is a capital F. This is okay. So I misspoke. Let me first find the cumulative the marginal cumulative distribution function of x, of the x variable. So what do you get? That would be the integral from minus infinity to x. We integrate all over the entire y variable, f of xy dx. But now dx dy, or maybe it's dy dx I should be doing here. Yep, I have to integrate dy first. I'm integrating the y variable away. Okay, so now it's going to depend upon whether x is smaller than 2. Remember, we're on a rectangle. Here's our rectangle. X is going from 2 to 6, and y is going from 0 to 5. So this is our rectangle. So now if x is less than 2, this is not going to be very interesting because the integral is going to be 0, so we're going to get 0. If x is greater than 6, we're going to get 1. So the only cases that we care about are the integral that x is between 2 and 6. So what we're going to do is we're going to take, this is going to be equal to the integral from minus infinity to x. Now y is supported between 0 and 5. So we're going to be integrating from 0 to 5. And then the function 2x plus y over 210. I'll bring the 1 over 210 outside. Dy dx. Okay, so this is 1 over 210 minus infinity to x. So we're going to be integrating from 0 to 5. And by the way, yes, okay. By the way, it's not minus infinity. It doesn't. We can also, the lower limit of integration for the x variable is given by the minimum value of x where the function is non-zero. So it's 2 to x we have to take. Okay, and I'm already using the variable, so let me use a here. So this would be 2 to a. Okay. All right. So it's minus infinity to a becomes 2 to a. Okay, so let's find the antiderivative with respect to y. So that's going to be 2xy plus y squared over 2. And y is going from 0 to y equals 5. And then we have to integrate that result with respect to x. Well, this is 1 over 210. The integral from 2 to a of what? Well, we're going to stick in y equals 5. We get 10x plus 25 halves. And the value at 0 is 0. And so we have to integrate this result with respect to x from 2 to a. So you're going to get 1 over 210 times the antiderivative of 10x is 5x squared plus 25 halves x, where x is going from x equals 2 to x equals a. And what do you get? You're going to get 1 over 210, 25 a squared plus 25 halves a. Then we have to subtract off the value at x equals 2, which is minus 20 minus 25 minus 25. So in other words, I'll write the answer up here. We're going to get the value of this double integral in the end is going to be 1 over 210, 25 a squared plus 25 halves a minus 45 if a is between 2 and 6. So that's what you get. All right. That's the so you end up calculating lots of double integrals. Okay. All right. Okay. We can also compute by differentiating, by the way, uh, the 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 density function itself. So that would be f sub x. We would just differentiate this answer. So f sub x of a is the first derivative. You would get 50a plus 25 halves, and that's for between 2 and 6, and it would be 0 otherwise. So that would be, that's how you compute that. Okay, so that's an example. I'm going to try another kind of example that's in the text. It's problem 1E. I'm going to need some space for that. So the idea of the example 1E is to consider a circle of radius, or a disk of radius r. So a disk of radius r in the plane. Okay, and now if you have a point in the plane somewhere and you have some region in the plane, I don't know, some region like this, the probability that that point lies in the region, let's call the region E, the probability that that point lies in E is going to be uniform. It's going to be uniform in the point, in the sense that the probability density function, f of xy, is a certain constant as long as the point xy is in the disk, and 0 if it's not in the disk. Okay, so the question is, what is the constant, right? So what's c? That's the first question, and there are 4 parts to this example. So we can calculate that as follows. We know that the integral over in all of the plane R2 of f of xy dA has to be 1. That's one of the properties of the joint density function. On the other hand, the joint density function is uniform in this sense, and so it's got to be given by the integral over the disk of radius r of the value of the function on that disk, which is constant dA, and that's c times the area of the disk. That's one of the, so what is the area of the disk? The disk has radius r, so c times pi r squared. So c times pi r squared equals 1, and because of that, we see that c is equal to 1 over pi r squared. So we now know what the function looks like. So now I'm going to go to part 2 of the question, part B of the question, which is to calculate the marginal distributions of x and y. Okay, so I need a new screen for that. So let's find, in part B, find f sub x and f sub y. So how do we do that? Well, let's just first of all start with f sub x. That's by definition, we have to integrate away the y variable. So that would be f of xy dy. This is always true. And we have to sum up overall every y, all the values of the function at every y. And that's the same as integrating. Okay, and then now the point is that this function f of xy, remember, is given by the constant c, which is 1 over pi r squared, if xy is in the disk of radius r, at 0 otherwise. So we see that this is the same as the integral. The integral of its integral is supported. Okay, so let's draw a picture. We're integrating over y. The only values of y which matter are those which. So if this is a point xy, we have to integrate between this minimum point and this maximum point. So y is going from negative the square root of r squared minus x squared to the square root of r squared minus x squared. Because outside any point xy outside the disk gives you a value of 0. So it's negative the square root of r squared minus x squared to positive square root of r squared minus x squared. And then the function on that strip, on that line segment, is given by the constant, which is 1 over pi r squared. And we're integrating with respect to y. And so if we do that, we're integrating a constant. You get 1 over pi r squared times this two copies of the square root of r squared minus x squared. So that's the, we can rewrite this as 2 times the square root of r squared minus x squared over pi r squared. So that's the answer for the marginal distribution function of x. And similarly, the marginal density function, I should say, for x. The marginal density function for y is given by symmetry. It's just the same thing. We just replace x by y. So that's part B. Okay, so let's move on to part C. Part C is a different sort of question. What is it? Part C is about the following. So find the probability of the distance of a point xy being to the origin, less distance to the origin. I'm not saying that right. Distance from xy. Distance from xy to the origin to be less than or equal to a. So this is the probability of a distance of any random point chosen being less than or equal to a. So what is that? Okay, so this is not hard. It's just interpreting what this is meaning. Well, this is the same thing as the probability. What's the distance formula tell you? It's the probability that x squared plus y squared is square root of that is less than or equal to a, or equivalently, the probability that x squared plus y squared, is less than or equal to a squared. Okay, so what does that mean? Well, this is fairly simple to compute because what is that? This is you're asking whether x squared plus y squared is less than or equal to a squared. So that would be inside the disk of radius a now. So that would be the same thing as the value of f of xy dA over the disk of radius a, which is the same thing as 1 over pi r squared remember that remember that's the same thing as the double integral over the disk of radius a times the value of the function. And the value of the function was given by 1 over pi r squared. And so that's the function. It's a constant function on the disk of radius A. A is less than or equal to r. And that's the same thing as 1 over pi r squared times the area of the disk, of radius A. And that's the same as pi a squared over pi r squared, which is given by a squared over r squared. So that's what actually the answer is for part C. Okay, so we have part C. And now, so let's call, so this actually is given by a random variable. Let's call this random variable D, the square root of x squared plus y squared. It's a random variable in itself. So we've just shown that the probability that D is less than or equal to A is given by a squared over r squared. Okay, so now we go to the last part of the problem, the example, which is let's find the expected value of D. Remember, D is given by D is a function on the sample space. It's going to be given by the square root of x squared plus y squared. So find the expected value. So what is the expected value given by? Well, this is given as follows. So first of all, we know that f sub d, we've computed, we computed in part C, we saw that the probability that d is less than or equal to a is given by a squared over r squared. But this is the same thing as the cumulative distribution function of the random variable d. So we can actually differentiate. If we differentiate, we get f sub d lower, that's the density function, is given by the derivative of a squared over r squared, which is 2a over r squared. Okay, and this is for a being between 0 and r, obviously. So then the expected value of the random variable d is the integral over the disk, which is the disk of radius r. That's the integral from 0 to r. It's not the integral of the disk, the integral from 0 to r. A is going from 0 to r. It's the integral from 0 to r of the function, which is 2a over r squared times, well, I should write 2x over r squared, and then we have to multiply it by x, of course, because we're getting an expected value here we're taking. And this is the integral from 0 to r of 2x squared over r squared dx. And you can integrate this and you'll get 2/3 x cubed over r squared from x going from 0 to r. And this turns out to be, when you evaluate it, 2/3 r. So there you go. We just computed, we just computed the expected value of the random variable d. Okay, so that's it. We're done for today.